So, this lecture is the continuation of the variable area adiabatic flow, and we will try to see if the change in area can be represented in terms of Mach number. Okay, that is our aim. So, I will write the equations which we had seen the other day. So, the first equation which we seen is this. And okay. So, we will try to see how these quantities vary with respect to Mach number. So, if I take d v by v by dA by A, this will vary according to this equation, which is going to be some discontinuity happens at m equals 1. So, you would see something like this. So, if I have m in my x axis and this quantity in my y axis, I would get something. So, at m equals 1 there is something that is happening, which we had seen at m equals 1, there is no area change. So, can we use that information to get a reference value, or can we represent the changes in area in terms of m at that area where there is no change in area due to the velocities. Okay. So, that is our aim. So, if I plot m versus A, I would have a minimum at m equals 1, because that is the value where dA is 0. So, my velocity would also go something like this, and the density would come down something like this. So, this is my area, this is my velocity, this is my density or pressure. Okay. So, we will use these information whatever we have learned in the other class to evaluate the changes in area. So, this happens for some arbitrarily shaped body whose area is changing. We have assumed Q to be 0, W is to be 0, and evaluating this. And these flows are, we have also used the energy equation to get this relation. So, with this condition is what we are going to evaluate the area changes. So, for some particular area ratio, can we describe this in terms of Mach number? So, I would start for an isentropic flow. Some flow at section 1, section 2. How did we see the process in the TS diagram? we because it's an isentropic flow, we have 1, so let us say 1 has gone to 2 isentropically. Associated with 1, I have a stagnation point, with 2 also I have a stagnation point. Since it is isentropic, T01 equals T02 and P01 equals P02. Okay. So, if I use that information, T1, we have T01 by T1 to be 1 plus gamma minus 1 by 2 M1 square. Likewise, point 2 have this relation. Okay. So, this is the isentropic process that happens at state 1, where the fluid is taken to a velocity 0 isentropically. So, this relation holds. The same thing happens at station 2, this relation holds. Because we know T01 equals T02, I can rewrite this equation in terms of T1 and T2 alone. Okay. So, this we have assumed W q equals 0, W is equals 0. Okay. And we have also seen P01, P02 by P01 to be e power minus delta S by R, which is now assumed 1. So, your P02 is same as P01. So, this is isentropic. So, you can use isentropic relations here to find, say, P2 by P1 equals T2 by T1 to the power gamma by gamma minus 1, which again you can write it in terms of M1 and M2. But now, if it is not isentropic, so let us consider a non-isentropic flow. So, I have a flow here. My ratio P1 by P2 will be a function of M1, M2 and delta S, and of course, gamma or R. Okay. If that is true, then my A1 by A2 also depends on M1, M2 and delta S. My m dot is constant. So, I can write rho 1 A1 V1 equals rho 2 A2 V2. Assume 1D flow. So, if I want to find A1 by A2, I would write rho 2 V2 by rho 1 V1. Now, I substitute rho 1 and V1 from perfect gas relation. So, my A1 by A2 is replaced by rho 2 as P2 by R T2 multiplied by R T1 by P1 into V2 is replaced as M2 into A2 is gamma R T2 divided by M1 dot gamma R T1. Which gives me a relation P2 by P1 into M2 by M1 into root of T1 by T2. So, between the process P1 and P2, I have this. There is an entropy change between location 1 and 2. P02 by P1 is 1 plus gamma minus 1 by 2 M2 square to the power gamma by gamma minus 1. Likewise, I have P01 by P1 equals 1 plus gamma minus 1 by 2 into M1 square to the power gamma by gamma minus 1. Now, I use these three relation to write P2 by P1. So, P2 by P1 P2 by P1 is P02 by 1 plus gamma minus 1 by 2 M2 square to the power gamma by gamma minus 1 into P1 is 1 plus gamma minus 1 by 2 M1 square to the power gamma by gamma minus 1 divided by P01, which I replace it as P02 by P01 into 1 plus gamma minus 1 by 2 M1 square divided by 1 plus gamma minus 1 by 2 M2 square to the power gamma by gamma minus 1. So, I have taken this two relation, I divided 2 by 1. So, this is dividing equation 2 by 1. Now, I replace P02 by P01 with this relation. So, my P2 by P1 is 1 plus gamma minus 1 by 2 M1 square divided by 1 plus gamma minus 1 by 2 M2 square to the power gamma by gamma minus 1 into e power minus delta s by r. So, this is the pressure ratio P2 by P1 with this. So, if it is an isentropic flow, this is 1 and hence you would get this relation, which is same as what you have got from your isentropic relation from T1 and T2. Now, I substitute this into this. T1 and T2 anyway I can get it from that relation. Okay. So, there is no Q, no Ws. So, T1 by T2 is this equation where you have obtained using the isentropic relation, but P1 by P2 there is a irreversibility and hence you have to use this equation. So, I am rewriting that equation here. A1 by A2 is P, instead of P2 by P1 I replace that with this equation. Minus 1 into m2 by m1. Now, root of T1 by T2 I use this equation, which T1 by T2 is 1 plus gamma minus 1 by 2 into m2 square divided by 1 plus gamma minus 1 by 2 into m1 square, which into delta e power minus delta s by r. So, this I can reduce it further to 1 plus gamma minus 1 by 2 m1 square divided by 1 plus gamma minus 1 by 2 m2 square to the power gamma by gamma minus 1. There is a 1 by 2 here, there is a 1 by 2 there, that is root of T1 by T2. So, there is a 1 by 2 there. So, this would be minus 1 by 2. So, gamma by gamma minus 1 minus 1 by 2. So, this would be gamma minus 1 into 2 gamma minus gamma plus 1. So, this would be gamma plus 1 divided by 2 gamma minus 1. So, this exponent is gamma plus 1 divided by 2 gamma minus 1 into m2 by m1 into e power minus delta s by r, which is my a1 by a2. So, my area ratio is a function of m1, m2, gamma and r and delta s. So, it depends on the fluid m1, m2 and your irreversibility. So, if this is the area ratio, you can try to see if there is a reference quantity with this. So, I am going to introduce a new reference quantity which is called your A star. The star condition is like our stagnation point. Star condition is when fluid is isentropically taken to m equals 1 condition, which means in the TS diagram from point 1, so I have a state 1, I take it to velocity 0 is my stagnation point. So, if I take the point isentropically to V equals 0, then I get my stagnation point. So, this is my m equals 0. Now, instead of m equals 0, if I take it to m equals 1, so let us say it is somewhere here, then I have my star condition. Okay. So, I take it isentropically, that is very important. So, if you can actually take the flow to m equals 1 in 100 different ways, but the one that you are talking about is when it is reduced to m equals 1 or or increased to 1 m equals 1 isentropically. So, if you do that, that is your star condition. So, what is your star condition? So, we will try to understand what is our star condition. So, we use this relation to evaluate further. So, let us say this star condition can be present in the flow or it can be completely imaginary point. Okay. So, if it is a converging diverging nozzle, your star condition is the throat area where your dA is going to be 0 and your m equals 1. So, that is also your star condition. We will come to that in a few lectures from now, but now let us concentrate on this arbitrarily shaped dA value. So, this is 1. So, along there is a Mach number associated with the station 1, this is a 1D flow. Now, I take this fluid to an imaginary value where m equals 1 and that value is your star condition and that area is your A star. Okay. So, the area associated, so if I write A1 by A2 as this and I take A2 as my A star, meaning my M2 is now 1. Okay. So, I substitute that into our relation which we already know. So, I take A1 by A star 1 plus gamma minus 1 by 2 m1 square divided by 1 plus gamma minus 1 by 2 multiplied by 1 to the power gamma plus 1 divided by 2 into gamma minus 1 into m2 is 1, this would be 1 by m e power delta s by r. Now, I have taken it isentropically to star value. So, this quantity is now 1. 1. So, that relation so, for any value, any location, I can remove the suffix 1. So, my A by A star is a function of m and gamma. Okay. Like what we had before, my P0 by P or T0 by T, which is also a function of m and gamma. So, if I know the Mach number at any location, I can find these ratios. So, for any given Mach number, I have one ratio. Whereas the converse is not true. For any value of A by A star, I can have 2 Mach numbers, because now this is in m square. Okay. So, we will see, we will do some problem and see what this. Yeah, what did we say? Eh? No. It is a quadratic, so it can have 2. It did not, I did not mean 2, I did not mean negative values. It is a quadratic in my m, so it can have 2 values. So, it has 2 values. So, one can be subsonic, one can be supersonic. We will see, when you do a problem, we will see. So, this brings in something called a gas table, where I can write my m and then I can have my A star or P0 by P and T0 by T, etc. for a given gamma. Okay. So, in the numerical solutions, we will use the tables and try to evaluate these quantities to a problem similar to what we had done before. So, in this lecture I have introduced a new quantity, a star value, a star condition, where the fluid is taken to imaginary point where the Mach number is 1, which means the velocity of the fluid is equal to velocity of the sound at that particular condition. This reference is something similar to your stagnation reference. We will see in the next lecture, we will see further information on star conditions, okay, how we can define what is the relation between T star, V star, P stars and other things.